So this is white light passing through a dispersive prism, and this is a visible spectrum. From about 420 nanometers in the violet, through 500 nanometers in the green, 580 yellow, 610 orange, and 650 red. And some of the slides are going to have this along the bottom axis. So how dependent are we on colour? What do you think? Do we depend on colour a lot or a little?
Lots.
Lots? Okay. So this is a scene without colour, and this is a scene with colour. So if you look at this scene, can you tell me what fruit this is?
Apple.
This one? This one?
Apple.
This one?
Apple.
So you get the point. Chicken? So if I change the colour, you can see immediately which fruits are which. So colour is important because it helps us to discriminate objects from their surroundings. But how important is it? If I take this scene and split it into its achromatic or monochromatic components and into its chromatic components down here, you can see that most of the details contained in the achromatic image. The chromatic components by itself provides relatively limited information. The detail in both space and time is really contained within the achromatic information. So I'm setting myself up for failure at the beginning because I'm telling you colour is not that important. So how do we see colour? An image of the outside world is projected onto the rear surface of the eye, the retina. It's inverted. It's projected by the lens and the cornea. This is the rear surface of the retina. It's carpeted with light-sensitive rods and cones. This is the centre of vision, where there are just cones. L cones shown in red, M cones shown in green, and S cones shown in blue. There are three types of human cones: long wavelength sensitive, middle wavelength sensitive, and short wavelength sensitive, and they're responsible for daytime achromatic and chromatic vision. There's one type of photoreceptor responsible for nighttime vision, the rods, and that's achromatic. The rods are much more sensitive than the cones, and they're designed to operate at low light levels. From absolute rod threshold, where you can see just a few photons, up to where rod saturation occurs, just below indoor lighting. The cones are sensitive over a much larger range, from cone threshold up to damaging light levels, bright sunlight. With the rod vision, we see this image here in poor detail. We have high sensitivity and we see no colour. And you can experience this yourself if you go out at night and darken out for 40 minutes. You will see things with your rods. And when you do that, you'll see something like this. You'll see no colour and poor detail. With the cones, you see colour and detail. Your sensitivity is lower, and remember again, it's responsible for achromatic and chromatic vision. The light-sensitive photopigment is contained inside the rod and cone outer segments here. This is a blow-up of light passes, by the way, through the neural layers to the outer segments. Here's a blow-up of the cone outer segment. Here's a bigger blow-up, and this is the light-sensitive opsin. It's got 7 transmembrane alpha helices, and sitting inside is the important piece, the chrome 4. And the chrome 4 is 11 cis-retinal. It's a molecule. It's bent here between the 11th and 12th carbon atom. So when a photon is absorbed, all that happens is the molecule straightens. It untwists. And that's the first step of the visual process. The change from 11 cis to all trans. And that triggers the transduction cascade, which leads to vision. The important thing about this is it's like a switch. It's all or nothing. A photon's absorbed or it isn't. But whenever photon's absorbed, it has the same effect. So this is a univariate process. It's colorblind. And that means that color vision at the first stage in your retina is relatively simple. But what does univariance mean in practice? I'm going to use M cones as an example. And here's an M cone. Here are some photons. And crucially, the effect of any absorbed photon, whatever its wavelength, is independent of its wavelength. So if you look at the output of the M cone, you can't tell which wavelength has been absorbed. So all the M cone photoreceptor does is effectively count the number of photons that have been absorbed. What does vary with wavelength is the probability that a photon will be absorbed. So a green photon is much more likely to be absorbed than a red photon. And that's reflected in what's called the spectral sensitivity function. And here is an M cone spectral sensitivity, wavelength along the abscissa, and sensitivity along the ordinate. And this is in log units. So low sensitivity down here, you need more photons to have an effect. High sensitivity up here, you need less photons to have an effect. So you're more sensitive in the green than you are in the red or in the violet. And we tend to use log scales for these graphs, because that allows us to emphasize the detail in the tails here. So if you imagine the sensitivity of these photons, in order of sensitivity, you're most sensitive to the green and least sensitive to the red. Now if you have three lights of equal intensity shown by the height, and you look at those, and they only differ in intensity. They have no colour differences. If you increase the intensity of each to compensate for the sensitivity loss, so you make this one brighter, then these four lights look identical. So the point is that with a single photoreceptor, you're colourblind. All lights look the same colour, but different intensity. So, if a light gets brighter, then it could get brighter because it's been made more intense, or because you've changed the wavelength to one you're more sensitive to. If it gets dimmer, it could be because you changed the wavelength to one you're less sensitive to, or you've made it dimmer. You don't know which of those two things has happened. So with only one photoreceptor, we would be colourblind. And examples of that are blue cone monochromats and other cone monochromats, and you can experience it yourself at night with night vision. Your rods provide an achromatic colourblind signal. So people with normal colour vision have three cones with different spectral sensitivities: S cones, M cones, and L cones, which peak at 441, 541, and 566 nanometers. And these three cone photoreceptors are the basis of our colour vision. So, the colours we see in the screen, in this picture, are they mainly a property of physics or biology? What do you think? Biology? Physics? Physics? So it's mainly biology. So if you see a yellow patch of light, it could be made up of yellow light or a mixture of two lights, green and red. And we can't tell the difference between those two lights. They're called metamers. Metamers are pairs of lights that are physically different but look perceptually the same. And there are many different metamers. Red and green combine to make yellow, and this is not art, this is adding lights together, so it's not subtractive colour mixing. If you add together red and blue light, you see purple. If you add together green and blue, you see a cyan. If you add together all three, you see a white. Or you would do if the projector was better. So we knew about this before we knew anything about the underlying biology. In the 19th century, experiments showed us that colour vision was truly trichromatic. And trichromacy means that the colour vision, the input to the visual system is relatively simple. It is a three-variable system. You can define colours in terms of three numbers. And it's exploited in colour television, and in this projector, if you look very closely at colour television, you can see individual dots of light that are brighter or dimmer. Or in more modern TVs, you see rectangles or different structures. You can't see the differences because you spatially mix them, because your eye can't resolve the individual pixels. So if the three primaries are bright, you see a white. If you just see red and green, you see yellow. If you just see red, you see red. So all the colours you see on this screen are made up of a mixture of three different lights. And it's been used in painting. Here's a pointless painting by Georges Seurat. And if you look more closely at the painting, you can see it's actually made up of small blobs of pigment. And this was an attempt to do additive colour mixing in painting. And this was done in the 19th century. So why is human vision trichromatic? The main reason is we have 3 cone types, S, M, and L, but also each one produces a univariate output. So if each photoreceptor is colourblind, how do we see colour? Or how is it encoded by the visual system? Well, if a light changes from green to red, then because the M cones are less sensitive to red, the M cone signal goes down, but the L cone signal goes up. If a light goes from red to green, the M cone signal goes up because the M cones are more sensitive to green, and the L cone signal goes up. So we encode colours by comparing outputs of the 2 cone types, or the 3 cone types. So each cone type is colourblind, but the way the signal changes as the colour changes is different. And that allows us to encode colours. So colour is encoded by the relative cone outputs. A blue light produces a bigger signal in the S cones, less in the M, less in the L. A green light most in the M cones, and a red light most in the L cones. And various mixtures produce different ratios. So a purple light will produce the biggest output in the S cones and the L cones. So that's the way colour is encoded at the first stage of vision, trichromatically. And just to point out, most mammals, including dogs, are dichromats. They're missing the M cones, so they see the fruit stand as something like this. So bulls don't see red very well. They're not. It just looks like a shade of yellow. Trichromacy developed relatively recently in our history. In old world primates, it was a gene duplication which duplicated the L cone to make an LM cone photopigment. And it's thought to have arisen because with only 2 cone types, we see something like this in the forest canopy, but with 3 cone types, you can see the fruit in the trees. So it is an advantage. But it's relatively recent. It occurred before Africa split from South America, and occurred in the old world primates. So, that's what happens at the first stage at the cone level. What happens after the cones? And what happens in the retina? This is the processing stream in the retina. The signals, the light's absorbed by the rods and cones, and the signals transmitted to the bipolar cells, ganglion cells, up the optic nerve to the cortex. But even in this stage, the cone signals are re-encoded. And we can work out what sort of things happen by just doing a thought experiment, by looking at colour phenomenology. So if you imagine a single patch of light, a single colour, surrounded by a dark surround, just try and think of which colours can coexist in that patch. And if you have a trichromatic code, then any pair of colours should coexist. You should be able to see a reddish green or a bluish yellow. So, this patch of light here, does it look red and yellow at the same time? Yeah? So, reds and yellows can occur in a single patch. Does this light look reddish and bluish at the same time?
Yeah.
Yes. But now if we combine red and green, we don't see the 2 colours in the same patch. A red and green together make a yellow. So we don't see a single patch of light as a reddish green. And we also don't see a single patch of light as a bluish yellow. We see it as white or grey. So there are pairs of colours that apparently don't coexist. And this led to a theory in the 19th century by somebody called Hering, in which he supposed that the encoding was such that red is opposed to green. So something can be red or green, but not both. Something can be blue or yellow, but not both. And the trichromatic theory of Helmholtz and the opponent theory of Hering were competitors. But if you look at the responses of these cells, you find colour opponency. And you find colour opponent red-green cells, where the L and M cones are opposed. So this is plus L minus M. And you see these various 4 types of cells, where L and M cone signals are opposed in the retina. And you also find cells in which the S cones are opposed to L plus M. So the colour phenomenology has its foundation actually in the neural circuitry. Although this is a simplification, you find it actually in this next stage of vision in the retina. So the first stage of vision, the cones, is trichromatic, and the second stage becomes colour opponent, where the differences in the cone signals are encoded. So what about achromatic vision? Well, again, I've already said most of the detail is encoded in the achromatic signal. And there is an important pathway in the visual system, which is effectively L plus M, which encodes detail in space, motion, and also fine spatial detail. And Lewis is encoded simply by adding together the L and M cone signals. So if you add together 2 univariate signals, you end up with a univariant colour-blind achromatic system. So colour is in many ways secondary to luminance. So here is the colour scene again, and I want you to adapt to this coloured pattern. And I want you to stare at that cross, please. And then I'm going to do something. I'm going to keep staring at the cross, and I want you to tell me what I've done. So I'm going to build up an after image, and the after images are going to be the complementary colours to the ones you're looking at. So where you see a purple, you'll see a green, and so on. So are you ready? Keep looking. So what did I do? Thank you. So I just changed the, I just put up a black and white achromatic image, and the colour filled in the detailed image. So this fuzzy coloured image very much fills in the detailed monochromatic image. So the achromatic image is sort of leading colour image. And just to show you it's not memory colours, if you look at this image, look at the cross, you're going to see some very unappetizing fruit. Okay. So, this is also an example of how colour fills in. These borders are simply chromatic borders in opposite directions, but this whole central area here, or peripheral area, fills with colour. This looks slightly blue, this looks slightly yellow, slightly green, slightly yellow, and orange. And these things, the colours tend to fill in borders. And here too, this is the wave-like colour illusion. This yellow appearance is simply filling in the sinusoidal wave. It's not actually there. And here's neon spreading, where you see this whole circle here as slightly tinted. So colour very much fills in the achromatic signal, the achromatic image. So that's what happens in single patches of light. But what we see in colour is much more complex, and it depends not only on the trichromatic code and colour potency, but also depends on what occurred before you see the colour, and also on which colours surround the colour. So we're going to start off with a colour after effect. If you look at this cross here, again, we're going to develop an after image, and let it build up a little bit. So you're going to see the complementary colours where these colours were. And if you blink, the colours should come back and look vivid again. So here we go. So the colour after image is fairly strong. And here's another example, for which I have to thank Media Fire. If you look at this lady's nose, fixate on the nose, please. And the complementary of that slightly blue black is actually a flesh tone. So this is apparently a famous Indian actress. And again, if you blink, it will come back. So, if you look at the cross, what do you see? You see a green light. Is it really there? No. If you follow it with your eyes, it disappears. So what you're seeing there is an after image moving around. Okay, contrast effects. These top and bottom squares are identical. If you surround them with colour, they change their appearance. So this green induces a red colour, this red a green colour, this blue a yellow colour, and this yellow a blue colour. So you get contrast effects where the surrounding colour induces opposite colour in the centre. And again, if you see that. In this example, these rings are actually identical, but because they're surrounded by different colours, they're very different. You see that? That's what they really look like. These are contrast effects. And that was used in art by many artists. The red and green contrast here, the blue, yellow, and the red, green here, which enhances the appearance of the colours. Assimilation is where, on a small scale, little dots actually combine, add together. So if you surround these with different colours, they change in appearance. So here, if you surround them with red, they look slightly redder. If you surround them with green, they look slightly greener. And similarly here and here, you get these colour changes. And the stronger effect here is the Munker illusion, where these reds change in colour depending on which bar abuts them. Okay, now I'm going to finally confuse your brain. And I'm going to show you a list of words, and the colour words, and they're in different inks. So what I want you to do is to say to yourself as loud as you like, the ink colour, not what the word says. Are you ready? Okay. Okay, that's not so fast. Okay, that's fairly easy because the two are the same. Okay, you ready for the next one? Here we go. 3, 2, 1. That's pretty bad. So this is known as the Stroop effect, and you're getting an interference between the colour word and the ink colour, because at some central location, the information about the colour word is arriving before the information about the ink. You get a conflict. Okay, I'm sure a lot of you have seen this. So, hands up who sees it as blue and gold. And who sees it as black and something else? Black and... White and gold? So, this caused quite a media stir at the time. So, it's ambiguous. And it depends on the assumptions you make about the colour of the illuminant, what the colour of the light source, or about shadows. And it's very, confusing. And you can see an example of that here. I can't get this to work, but this square here is actually identical to this square here. This is from Beau Lotto. This one is illuminated by a blue light, so we assume it must be yellow. And this one's illuminated by a red light, so we assume it must be green. And this sort of idea about the illuminant and shadows changes our perception a good deal. So, thank you very much.